Hi everyone, welcome to today's webinar. The topic for this webinar is Developing an Energy Storage Project, a Technical Perspective. This webinar is a presentation of the Energy Storage Technology Advancement Partnership, also known as ESTAP. ESTAP is managed by the Clean Energy States Alliance and is supported by Sandia National Laboratories and the U.S. Department of Energy. Our host for this webinar is Todd Olinsky-Paul. Todd is a project director for ESTAP with the Clean Energy States Alliance. And we have two excellent guest speakers with us today from Sandia. Before I pass it over to them, I'd like to go over a few quick housekeeping notes. All of our participants for this webinar are in listen-only mode. You have a couple of options to join the audio portion of this webinar. You can either call in using a telephone or you can connect using a computer mic and speakers. There's some instructions there on your screen for how you can do that. A very important note, we ask that you please submit your questions as you think of them throughout the webinar, and we will read through your questions as they come in. We'll get to as many as we can at the end. We're going to try to save at least 15 minutes for a Q&A following the presentations. So again, please type your questions in as you think of them. Don't wait until the end of the webinar to submit your questions. A final note, this webinar is being recorded. You'll find a recording of this webinar as well as all of our previous CESA webinars archived on our website at cesa.org/webinars. So with that, I'd like to pass it over to our host for this webinar, Todd Olinsky-Paul. Todd?
This is going to be an excellent webinar. It's one in our series of ESTAP webinars, so I'll just do a brief introduction of ESTAP and CESA, then I'll introduce our speakers, and we'll go right on into the webinar. So CESA is Clean Energy States Alliance. We are a nonprofit located in Vermont. We work with states and municipalities all over the country to help them with clean energy programs and policy development mostly, and we also do some work under contract with U.S. DOE and National Laboratories. This is one such project. It's called the Energy Storage Technology Advancement Partnership, or ESTAP, and it's conducted under contract with Sandia National Laboratories and funded by U.S. DOE Office of Electricity. We're fortunate to have two speakers today from Sandia and extremely experienced in the deployment and development of energy storage projects. So we will introduce them in just a second. I just want to say before we do that, if you could advance the slide, Samantha, that would be great, that as I said, we do a lot of work with states. We also produce publications, webinars, we speak at conferences. There are many upcoming events that you may want to be alerted to. If you got the link for this webinar from a colleague and you're not on our mailing list, go to our ESTAP webpage on the Clean Energy States Alliance website. You can see a screenshot there and click on the sign up for this mailing list button. If you would like to review prior webinars, and there are several years worth of archived webinars at this point, the menu on the left with the red arrow pointing at it shows you where to click to get to the webinar archive. Next slide, please. So without further ado, I will introduce today's panelists. We have Dan Borneo and Ben Schenkman, both from Sandia National Laboratories. Dan Borneo is an engineering program project lead and principal member of the technical staff at Sandia. He serves as the principal investigator and project team leader for the Department of Energy, Office of Electricity, Electrical Energy Storage Systems Projects Program. He has 35 years plus experience in the electrical power industry and holds both BSEE and MSEE degrees from the University of New Mexico in Albuquerque. He's also a licensed professional electrical engineer in the state of New Mexico and an expert, I say that from experience, expert in energy storage project development. We are also going to have Ben Schenkman, a senior member of the technical staff at Sandia in the Energy Storage and Microgrid Department. Will be speaking, and they'll be sharing the slide deck, so they'll be handing it off back and forth between them. Ben's current work involves microgrid control theory, microgrid assessments, physical security design, battery management systems, energy storage design implementation, distributed generation, and modeling distributed and renewable energy in the distribution and transmission systems. Prior to joining Sandia, he worked at Texas Utilities as a distribution engineer and at the Public Service Company of New Mexico as a bulk power engineer. He also holds BSEE and MSEE degrees from New Mexico State University with an emphasis in power engineering and deregulation economics. So if we could advance the slide, please. I just want to say, before I hand this off to Dan to begin the presentation, that I think Samantha mentioned, we will be taking as many questions as we can. This is a 1-hour webinar. We will stop at about 20 to start answering questions. So please type your questions in. There's a question box on your console. Do it whenever you think of a question or comment as the material goes by. Just go ahead and type that in so that I can compile those and we can be ready to address them immediately following the conclusion of the presentation. Okay, now I will turn this over to Dan Borneo.
Good morning, everybody, and thank you for joining. I just wanted to make one clarification on Todd's intro for me, or to me, is or about me, is that expert is not a word I like to use to describe myself. I figured you need at least 40 years to become an expert at something, so I still have a couple more years to learn everything I need to know, so maybe I could become an expert. So today we're going to talk about developing projects. You know, as the energy storage is taking off, we're finding that we're being asked to help people develop RFPs, et cetera, et cetera. So we put together this presentation to just give people some thought on what it takes to develop a project. I would assume people that are in the projects world know this stuff already. Now you're just adding this new technology, energy storage to it. So there's a little mystery, and hopefully this will help just alleviate some of the concern. So there's some acronyms. Everybody will have access to these presentations. So as I go through them, I might breeze through some of the sections, and but you could go back at your leisure and go over the presentation. So a little bit of advertisement of the Sandia Projects Group. So we work with the utilities, industry, states, academics, international and national. We provide third-party analysis. We support the development and implementation of grid-tie projects. And then what's in it for us is we basically go in and monitor, collect the data, do some analysis, and figure out, does it work? What are the economic benefits, and how do we make it better? And our end goal is to proliferate the use of energy storage on the stationary grid. And so our goal here with the states, in which Todd and I work very closely together on, is to have a pin in every state of the United States. And where we are right now is, you can see, we're starting, we're not quite there. And we just continue to keep working at it, and as funding becomes available, we do more and more projects. So the steps in the development of a project, are, in which we go into detail, are the project programming, the design, the procurement of the system, the construction, the commissioning and testing, which I should probably make that box a bigger box and a little bit more highlighted, and then into operation and the warranty and etc. So project programming. This is the stage where kind of figure out what it is you're trying to do. I've had received calls in the past where people say, I want to do an energy storage system project. Well, what problem are you trying to solve? Like, well, I don't know I don't know. I just want to do an energy storage project. Well, what you want to do is think about what problem you're trying to solve, do some initial analysis. Sandia is developing tools to help the industry do this initial analysis so you can figure out what applications you might utilize energy storage for based upon your situation in front of the meter, behind the meter, a vertically integrated utility, other types of utilities, municipality, what your rate structure is in your area. All these things go into the initial analysis, the charge and discharge cycle profiles, because this is going to really tell the vendors how the battery is going to work and how robust it needs to be. You know, what's the depth of discharge, how often are you going to cycle it, etc. And then you need to understand up front there if you're going to own and operate, or if you're just going to have somebody build it and then you purchase the electricity from them. So when you get into the project team development, you know, back in the day, it would just be a group of engineers sitting around a table. But those days are long gone. I was just thinking about this and just how much more communication and teamwork that needs to be involved in today's projects. And so you got, you know, as early as possible, and sometimes this depends upon your project delivery method below, which I will talk about, but eventually the people that I have listed in this first bullet are the ones that you need sitting around your table. The authority having jurisdiction, especially now, it used to be you'd call them up when you were done, bring them in, have them do an inspection. Well, since energy storage is new, there is a lot of consternation about its use and the codes, and Ben Schenkman will talk a little bit more about codes. And so at this juncture, the earlier you bring in the HJ, the better for you. Firemen, I had a long conversation last week with the firemen at a safety conference that Sandia put on, and it's amazing the questions that they have that I would never even think about as an electrical engineer. So having them, and the insurance men, because in some cases the insurance people will need to be involved in writing some type of policy for the system. And then you have your traditional, the commissioning agent, if it's not your maintenance people, and I kind of put an asterisk there because I always want that to be the maintenance people, because this is their opportunity to learn how the system works. And then you have your procurement, your safety, your utility. You have to have utility if you're going to be connected to the grid, and all the other people. So under project delivery methods, and one thing I should note, as I go through this, I was actually thinking more from the angle of design, bid, build, which that basically is you hire a design engineer who designs the system, puts all the specifications together, issues a bid package, what is then bid on, and then is built. The bid package is awarded, and then it's built. Another term for that is engineer, procure, construct. However, in some of the smaller projects, or it doesn't really matter if it's a small project or not, depending on the staff of the owner, maybe they'll want to do a design build, and basically where the owner then puts out the specifications, the scope of work, and then the vendors bid on it, but they will also own the design, the procurement, the construction, and the commissioning. And so that's all in one house. And then obviously if you're an owner and you just want to purchase, a lot of developers are developing projects with the intent of selling the electricity back to the owner. So some tools to when you're doing your process, RFI and the RFP. The RFI basically is throwing out information. Actually, we just did an RFI a couple weeks ago. Hey, here's our scope, here's our schedule. Is there anybody out there interested that can meet this? And then we get response back. Based upon those response, we then develop an RFP that kind of narrows it more down into what it is we want. We issue some specifications. We tell them what codes they need to follow. We provide them drawings of the system, of the area that we're going to put it. You give them any detail that you know at the time, and then this way they have information of which they can bid on. And then, you know, your procurement methods, you have a sole source. You know, if you have a partner and you work with them, you can, and your procurement allows this, you can do a sole source. You could also do the low bid wins. In energy storage projects that I've been associated with, I would not do that. I've never voted to do that because you do get what you pay for, and somebody could just try to buy a project whether or not they could perform or not. Best value is the tool or the method that I like, because there you look to a selection criteria. You can do apples to apples and make a better decision. And then a unit price for time material, that's one that could be used, but once again, you have to have partners that you can trust, construction outfits that you can trust, and you need to manage that a little bit more than, say, a best value. Okay, so a little bit of the technical stuff here. So where can you put the energy storage system? So you have 3 locations. You basically have at the generating station, you have at the transmission customer on the transmission, or you have on the distribution side. So any of these places can be utilized for energy storage. Some of the pros and cons in the business model is that it's centralized, utility-owned. The benefit all goes to the utility. Little or no benefit directly to the customer. At the distribution side, it's kind of a gray area. Economic benefit goes to the utility if they own it, but the resiliency goes to downstream of that distribution. And then the question here is, how do you monetize the energy storage? A lot of work going on in that area, figuring out how do you label this asset and how do you get paid for it, especially from the utility side. On the third party side, the one that comes to my head when I think of third party, I think of a big commercial industrial installation. Now there's a lot more work going on in residential energy storage systems, and there the benefit obviously is with the owner, with the customer, but the utility does gain some use benefit of the system, and that's all once again depending upon any type of agreement made with the utility. Maybe they'll come in and want to utilize this system and have some control over it. So some of the applications of energy storage, you got the power quality, reliability, UPS, and I'm starting to hit on this more and more, the UPS. Many industry customers have UPS systems, uninterruptible power supplies, maybe for a data area in their facility, or anything that cannot stand a momentary interruption. And so what I say is, hey, listen, if you're going to do a project and you're going to install a UPS, and by UPS I will make the comment that a UPS system, in my definition, is a unidirectional inverter. That means power only flows toward the load. It doesn't go back to the grid. I would say, hey, maybe look at an energy storage system, which is a bidirectional inverter. Power can go to the load or back to the grid, And that's very high level analogy there, but basically that's how it works. That maybe you could utilize that energy storage system. Well, in the UPS system, you utilize it 0.02% of the time. It's not used very often except in an emergency. Maybe you can utilize an energy storage system the other 99.8% of the time. So also you can use it for demand reduction. If we have time, I'll show a couple case studies where we actually used energy storage to decrease the peak for a utility. They were therefore then able to reduce their capacity payments to the ISO. You could also use it for energy shifting. This is mostly used in the PV, but it could be used for other things as well. And then you have generator support, where if you're running a generator, such as like if you're in Alaska or somewhere in a remote area, some island and microgrid type application, the energy storage could be utilized to reduce your runtime on the generator, therefore reducing cost in fuel and maintenance. So some of the considerations in the cost of an energy storage system project, you have your design, your permitting, your studies. You might have NEPA studies, you might have the power connection studies. God only knows anymore where you're located, what the governing bodies might ask you to study. Then you have your site and infrastructure work. Then you have your energy storage system, dollars per kilowatt, dollars per kilowatt hour. And one thing I didn't mention about that, back in your programming stage, you need to be thinking about what size do I really need, and what energy capacity do I need to get the most bang for the buck. And also you have your balance of plant, any air conditioning, fire suppression, lighting, etc. And then you have your construction installation cost, your commissioning cost, which a lot of times is not really known until it's too late, because you want to do a detailed commissioning of the system so you know that it's going to be safe when you start it up and run it. And then you have your warranty cost. Then your operating cost is, your efficiency factors, because energy storage systems are 70% and above efficiency, so you're going to be losing some electrons, some electricity, and if it's not coming from renewables, there's a price there. Then you've got your cycle life, your replacement cost, the cost to operate, maintain, warranty, and then debt service, and then last but not least, what do you do with it when it's met its lifespan? So some of the elements of an energy storage system, you have your storage system itself, you have a power control system, you have an energy management system, and then the balance of plant, whatever that might be. So I'm going to move along here because I think I'm starting to run out of time. So some of the energy storage types, you have capacitors, hundreds of thousands of cycles. So electric charge, you have flywheels, the kinetic energy, then you have battery. We're dealing mostly with batteries and some flywheels. And some of the batteries, you have the traditional lead acid, you have advanced lead acid. Advanced lead acid is basically taking hundreds of cycles of the traditional lead acid, and now they're getting thousands of cycles with the advanced lead acid. And lithium ion, which anybody who's been around anything knows that lithium ion is the flavor of the month or of the year right now. So most projects are lithium ion. We also have vanadium flow, which is an energy battery, basically 4 hours and above, great for. We have zinc, we have sodium sulfur and sodium nickel chloride, and we have aqueous sodium. And then just a little summary here of the lithium batteries. So right there I have 6 lithium batteries listed, and everybody thinks they're the same, but they're not the same. And this slide here shows the energy density, And as you can see, you know, the lead acid is down there at 40, and the cobalt battery is up there at the right-hand side. It's up there at 240 watts per kilogram, or watt hours per kilogram. And so when you look at the battery fires, et cetera, you're going to see that they're mostly the right two lithium-ion technologies. So the higher energy density, the more energetic they are, the more that when things go bad, things go really bad. So you have these other, like lithium titanate down here, much safer lithium-ion technologies, much lower density. And what that means is you need more of them to serve the same purpose as, say, the nickel cobalt. So project design. Once again, design, bid, build, or design, build, depending on what you're going to do. Are you going to hire your designer up front to help you put out a bid package for design build? Any shape or form, you should probably always have an engineer on your project from the get-go to either decide whether they will do the design and issue for bid, or they would just do a specification RFP to do a design build. Some of the things you need to consider: the site infrastructure, your point of connection, you need your one lines, all your electrical distribution, and then your balance of plant.
So continuing on, we have to first understand what the application of the energy storage system that we're going to do. So we need to optimize the kilowatt and kilowatt hour, and this is done by doing analysis. It also depends on the criteria that you're looking at. Maybe your energy storage is for resiliency, or you're trying to get an economic feedback on this one. So we need to have the study done before. In too many cases, we have people going out and buying the battery and then trying to figure out what they can do with it. So it's better to do the analysis up front to determine the size of the energy storage that better suits your needs. Once you've figured out the kilowatt and kilowatt hour, now we can determine what technology is better suited for this. You might determine that you need more kilowatt or power versus energy for shorter durations but need a lot of power. So you'll look at more like at the flywheel type technologies or capacitors, or maybe you need something that's more arbitrage and need more energy. So you're going to go to something that has a lot of energy but not a lot of power, maybe like a flow battery, lithium ion, lead acid. The other thing you have to consider are your environmental concerns. If you're out in Alaska, you have to understand that a lot of the pumps or something can actually freeze and pop. So you need to make sure you have HVAC for that. Or you might be in a place where it's very sandy and the silt is very fine. It can actually clog up filters. So you need to have specialized equipment out there for that. You also need to develop the sequence of operations for your application, such as if you're a microgrid type application, you have to know what to do from going from grid tied to islanded and vice versa. So you need to have the sequence of operations kind of honed in on. The next part is the energy management system, or we also known as a site controller. This is the control that sits on top of the energy storage system that gives it basically the command to put out power or absorb power. It's running the application for you that you have decided on, and you might even have stacked applications. You might be doing frequency regulation for a couple hours, and then you're switching over to an arbitrage type application. Also, the site controllers and the energy management systems can be tied into other distributed energy resources. So you need to make sure that EMS can work with all the different resources that you have in your grid. The other part is centralized versus decentralized controller. A centralized controller is basically you have a computer that controls all the different devices that you have out there, but it's from one point. A decentralized controller is the control is actually located at the actual device. So it's at the energy storage device. It knows what to do based off the input that it's getting at its terminals. It doesn't need outside input to control it. The next part is you have to determine, at your area, does the system need to be UL listed or have some sort of national recognized testing laboratory certification? And if it doesn't, you have to get buy-in from the AHJ on this one. The codes and standards that are required, there are many. I will go into a little bit. We have a list of that, and I will show that in a couple of slides. And the next one is your data acquisition system. We're showing here just a couple of information that you want to pull from it, such as the voltage, current, the power, and power factors. Other things are like the ambient temperature, temperature of the batteries. You want to look at the charge and discharge profiles that it's doing, and you want to make sure all your data is timestamped. And we'll go into that into the next slides here. So as you see on the screen now, is on the left side we have a normally operating system. The green means that it is on. The arrows are showing the power flow. We have energy storage on the right and PV generation on the left, and we have critical loads and non-critical loads between. And on the right side is if we had a utility outage, the battery is performing basically UPS backup to the critical loads. What we're showing here is where you want to start collecting your data acquisition for different points on the system. On the left, if you are doing like a renewable firming, you need to make sure your data acquisition system is recording the PV output, as well as what's inside the energy storage system and what's at the AC portion of your energy storage. We'll go into a little bit more detail here. So to look a little closer at your data acquisition system, what you're really trying to do is you're monitoring your battery performance. You want to make sure that when you asked it to turn on and it turned off according to your application. You're also looking at capacity fade over time. So at the very beginning of your project, you kind of do a capacity test because you want to see where your battery capacity is at that point. And then in your contract, you might have like after 10 years, you will provide a certain capacity. So your data is being used to make sure that they are meeting your specs at the 10-year mark, and you can do another capacity test at that time. Also, you're just looking at energy consumed and what was delivered. Did it do it when it was supposed to do it for your application? Important aspects that come to a data acquisition system is such as remote access to the data. You need to make sure that this remote access is cyber secure. You want to make sure that the data that you are remotely accessing is quality data and that no one's hindering it as it's coming to you. You want to make sure all the data that you're bringing in is time-stamped so you can do correlations between, let's say, the PV and the energy storage turning on and off. Sampling rates is a very large one here. If you're doing such items as frequency regulation, you need to have very fast monitoring. So your sample rates are going to be down there in the seconds or actually sub-seconds levels. If you need harmonics, you're actually in sub-cycle type levels. If you're doing more of an arbitrage, you can look at 1 minute and 5 minute data. So sampling rate also depends on what applications you are doing with your energy storage. And we also recommend having 30 days of onboard memory. This could be in the form of SD cards. And when you get the SD cards, you make sure you have 2 of them, because if you have one in there and something happens where you lose communication and you have to give that SD card to whoever's doing the data analysis, you want to make sure you have another SD card to put in its place while the other one's being analyzed. Some of these parameters, we do have like the voltage and currents, AC and DC, the battery, power. We have an exhaustive list here at Sandia. If you want a longer list, just please email Dan or I, and we can provide that to you. So here's a list of some codes and standards that may or may not apply to your energy storage when you're installing it. There are plenty of codes here, IEEE, UL codes, National Fire Protection Act codes. There's many here, and in the next slide we show a couple more. But for the list of all the codes and standards and regulations, and also a little bit of description on what they do and what they mean, you can actually visit the site down here on the bottom right here, and you can actually see a full list of that, the codes and standards for that. And these are just additional UL codes that we have in IEEE. So now we're going to get into the commissioning activities during the design. So right here, this is a very important one Dan was talking about earlier about the roles and responsibilities across the team. The first one is the integrator. This is kind of like the glue or the bridge between getting the system and handing it over to the operator. It's a very important position. They're kind of in the middle of everything. The engineering designer or architectural engineering firm are the people that are out there designing the system, the infrastructure to actually put into the energy storage system into the site. Now, as Dave mentioned earlier, the inspectors, the environmental safety and hazard representatives, first responders are very important to have at the beginning of the design phase, because as Dan mentioned, when you start talking to like fire marshals and stuff, there are stuff that you're not thinking about as an electrical engineer or maybe just a certain stakeholder, that they actually have processes in place that you need to meet. So there might be additional type designs that need to be put in place. The next we have the commissioning agent, which is typically like your facilities at your site. It could be a different commission. It could be a third-party commissioning agent. It just depends on who it is, but they need to be in the design review. If you're connecting to the utility, you need to be, have a utility representative there. The people that are providing the energy storage, they need to be present. You also need, if you already know who's going to be doing the construction at your site, it's not going out to bid for all the construction. It's actually you have a designated construction person at your site. They need to be involved. This is for the schedules. And the same thing with the commissioning aid. This is if it was not maintenance, you just need to have them at the table. And then while you're reviewing your design and stuff, you need to make sure you know why you have the certain power and energy rating that you need and what application are you meeting here. The parameters that the system needs to meet, not just electrical like 480 volt or 3-phase, but you need to make sure that it's meeting all the NEPA requirements, it's meeting all the requirements of safeties and hazards. It's just, you need to review and establish all your environmental safety and hazard requirements. You know, you just need to know what you have to have in place, such for the fire, or if you have leaks, you need to have all that put in place. So Dan, I'll turn it back over to you for the procurement activities.
Thank you, Ben. So procurement, right? Man, near and dear to my heart. So we talked about this a little earlier, whether to use the RFI, the RFP. So as you go through the programming, you know, what is it you're trying to do, what's your procurement method, what's your delivery method, and that kind of drives how you put this out for bid. And we went through the procurement methods of the sole source, etc. And also, you know, one thing when you're doing into the contracting phase is, you know, one thing we're kind of learning right now with some work we're doing is maybe having a performance clause for project and system. You know, project management, project delivery, if they don't come in on time, there might be some incentives for them to come in on time, or de-incentives. I don't want to use the word penalties because that's pretty hard to do, but you know, maybe some clause that kind of helps protect you and your money. Next slide, please, Ben. And so then the construction, you know, so during the construction management, you want to see that, you know, you want to make sure everything's going in safely. They're meeting the scope, schedule, and budget. What you don't want to have is some inspector go in after everything is done to do an inspection, only to find things wrong, and then develop a punch list and adds a whole bunch of time and maybe money to the schedule. What I always advocate is, if you have an inspector, they should be part of the construction management team, looking at things up front, early on, fixing the problems before they're finished, and then that will make a better project. So, you know, you have your design, your shop drawings, a design verification. Maybe your designer goes out and makes sure, even though everything's built safe and you know, everything meets code from the inspector's point of view, is it meeting the design as the designer designed it? So a lot of meetings, right? A change order process, if there are change orders, you need to have a process to keep track of that and who pays what. Then contingency plans and workarounds. I can't stress this enough. As a project manager, the first order of business was having a workaround or a contingency plan for any critical path item. And then, you know, obviously you got your safety, and you got your lockout tagout process. You know, all your safeties, which your program should have. Here at Sandia, we have a safety thing that's very thick, but I wouldn't advertise that for anybody else to use, but that's just the way we do our business. But you need to have a safety plan. And so with that, I'm going to turn it back over to Schenkman.
All right, so I want to go through this pretty quick here on the commissioning activities during construction. We have the factory acceptance test is basically what we do at the actual factory when you're just testing the battery and the different parts of the battery. So you want to make sure it turns on and off, and I would stress that you want to actually have the inverter and the battery at the same place when you're doing the factory acceptance test. You want to make sure the whole system kind of works before it comes out to your site. During these construction, you want to develop the startup procedures, the manuals and stuff, how to turn the energy storage system on. You want to develop your testing procedures. So we have a Panelists and Sandia have a testing protocol. If you don't know what type of testing procedures to put in place, you can visit this site and get the report, and it'll help you out. It breaks up different applications of what testing you need to do for each application. You also need to develop a checklist. So you want to make sure how do you verify that the design is right, it meets the codes, and then you want to start creating a punch list of items that need to be corrected. You also want to develop the training and emergency response procedures. If an event happens, what takes place to alleviate that, the emergency response for that. And then you also want to have, do you have strobe lights in place, smoke alarms, and what happens when that goes off. Here's just kind of an overview of the commissioning process. The goal is basically to ensure a safe and reliable system is installed and designed and is verified operational. What we have here on the right side is just showing like the factory witness test, or at the factory acceptance test is going out there making sure everything is great, make sure it has great workmanship. Then once the systems have been proven they can turn on and off, it's going to be brought out to your site and do another test. It's almost like a factory acceptance test, but now it's called an operational acceptance test. This is at the site looking at the different systems and the subsystems, making sure they work and they're reliable. This is the part where it turns over to your operation and maintenance group that will start to do the startup, and this is what we call a yellow tag, which is applied. At this point, the people that are doing the commissioning, they now own the equipment. They will do the startup, and they're going to do a functional acceptance test, which is what the application of the energy storage is. At this point, once the system has been deemed that it can function and is doing what it needs to do, it is then turned over to the owner. Once the owner has it, if the operation and maintenance people want to work on it, they have to go through the owner to work on it. So at this point, the owner is the one that owns the system. And then we go to a shakedown, which is typically this happens, it could be semi-annually, annually, is like turning off the actual power from the utility to the energy storage system, making sure it shuts down safely, and then when you restore power, that the system comes back in a safe mode. So we'll go into a little bit of the operational acceptance testing. Here, this is where we're talking about, we're just starting up the system, we're making sure everything works at your site. They do measuring to make sure there's no shorts, you're torquing down the wires, making sure that it's torqued to the right pounds. You're looking at the rotation and phasing so you don't have an A phase going to a B phase. And also the covers and barriers. So when you have exposed energized parts, you want to make sure they are covered. The barriers are not just like for panels and the system itself, but you might actually have a gate that needs to be put in place. You also want to do the controls test. This could be from the HMI that's on the system. When you're putting a PR2 command, it does, the energy storage does respond as needed. Same thing like, an E-stop, you want to make sure when you push it that that control actually works. You want to verify the electrical protection. You also want to test all your sensors out. And once you've done all this and you've showed that all the subsystems work, this is when it's turned over to the operation and maintenance people. So now they can start doing the startup process and do functional testing. So in the process, when you're doing the startup, basically what you're looking at is you want to do a record of the baseline when you turn it on. You want to make sure all the voltage and currents are right. You want to make sure that your meters, what they're putting out there, showing you this is the voltage and currents. Use another ammeter just to verify and make sure all your meters are calibrated. You want to perform an initial IR scan. Make sure you don't have any loose wires hanging around that are not torqued down right, because this can cause premature failures. You also want to do a capacity test. This is charging the system up to 100% state of charge and back down to 0% of state of charge at either 100% depth of discharge or at different ratings. And you're looking at the capacity. You want to do this about 3 times, and this will give you a baseline of what your system is, and make sure it meets your performance specs. That if you bought a 1 megawatt hour energy storage system, you're getting a 1 megawatt hour energy storage system. You also want to make sure that the efficiency that was quoted to you is correct. So you're doing the kilowatt hours out over the kilowatt hours in, and this will give your overall system efficiency. And if anything goes wrong, you just need to make a record of it. You also want to do, if you do have a site controller or you're doing this remotely controlled to the system, you want to test that out, as well as just make sure the data acquisition system is recording correctly. Make sure you're not having some weird sampling problems or data is not being timestamped correctly. Once we know that the system starts up, we have to go to the functional acceptance test, which this is just the function of the test, the system, what application you were doing it for. It might be multiple applications you'll have to test out here, but you're going to make sure all the components are working in subsystems, such as HVAC. You want to make sure your fire sprinkler systems are in place and they're working. All controls work. You want to make sure all your communication systems work, data acquisition's there. You want to make sure that all your operators are trained, and all your first responders are trained at this time too, so they know exactly what to do when an incident happens. You also want to have your warranties in place, and you also, like I said before, you want to log the baseline data that you have. At this point, once we know that the system is functional, we turn it over to the owner, and they take over from there, which now we do the shakedown process. This could happen as soon as it's turned over to the owner, or it might happen later on. Basically, like I was mentioning before, it's just the energy storage system's connected. We turn the power off. Does it shut down safely? And then once it's shut down, we turn it back on. Does it go to an idle state? Is it safe? Does not have any problems? If it does, you need to have them fixed. You want to make sure that all your alarms went off. So when the power went off, did you receive like a system alarm saying that AC voltage was lost? So you want to make sure that you are getting the faults and stuff that you're supposed to be getting. Once we've done the shakedown and we know the system's going and it's working, here's a couple additional things that might happen. You might need additional operator training if they didn't catch it the first time, or you might have some new operators. There might be additional training that's there. You might determine that the application that you chose in the beginning is not correct. So you need to change the application, but you want to make sure that the energy storage system that you have meets that application. If you bought it for arbitrage and you're going to try frequency regulation, you could kill the battery and you could void the warranty. So you want to make sure that you look at, you're doing a review, but it has to fit within the performance specs of your energy storage system that you bought. You also want to look at your data acquisition system. You want to monitor the system performance as the energy storage system's going. You wanted to monitor the capacity fade. It also helps with predictive maintenance. You might have cell voltages that are getting very low and it's driving down your system, so you want to make sure that you're looking at all your data points. You also want to make sure you are getting remote access and that the on-site storage is working too. You need to verify that you can pull out that SD card or USB drive or whatever you have in place, and it does have logging of the data on it. And then also make sure the system is being operated as designed. This is what I was talking about earlier with the application review. Make sure that if it was made for arbitrage, it's doing arbitrage. It's not trying to do frequency regulation or some other form of application. Just make sure throughout the time that you know if you have a change of a fire marshal or something, you know who to call and the numbers for that and what they do during an event of an emergency, and all the warranties. Just when something happens, who do you call? If something breaks down, which person you call? Is it the integrator or is it the actual vendor themselves? And I believe we are skipping over the case studies and going straight to lessons learned, which this will go back over to Dan.
Thank you, Ben. See if I can get this. Here we go. So lessons learned. So what can go wrong will go wrong. So basically have a contingency plan. Make sure you have your schedule allows for some float. So be aware of the time it takes to get the permitting, the contracts in place, any studies that need to be done. Commissioning plans always seem to be pushed off until it becomes a gate. So get after it early in the process. Get everybody involved that needs to be involved, and some people that you won't even think that need to be involved will pop up later on saying, well, why isn't I involved? And no, you can't do what you want to do because I don't know what you're doing. Then we talked about the performance clause. And so, try to protect yourself as best you can so you get the scope, the schedule, and the budget that you anticipated. And one thing I'm learning is when there's one finger pointing, there's three pointing back. So anytime you want to try to penalize somebody, it's going to be tough because everybody has a role to play in the success or failure of a project. So sometimes it's really hard to blame any one person. So this, just in summary, energy storage has its abilities. It could do things now that we didn't know that it could do. We're getting, it's becoming more and more mainstream, but we still got work to do coming from the science side of it with the cost, the reliability, and the safeties, and we're working on that. So with that, I'm going to go to my final slide, and Todd, I will turn it over to you.
Okay. Well, thank you, Dan and Ben. We are going to extend the webinar a bit because we're scheduled to end in 3 minutes, but we need to get to some questions. So if you're listening and you asked a question and you got a few minutes, stick around. We're going to do our best to get to them. So first question is in regard to warranties, and the person wants to know whether there are companies, I assume that means battery vendors, prepared to warranty the system for more than 10 years, and which technologies can provide warranties right now. And I just want to say, I've seen some recently that are offering a standard warranty of 5 years, which I don't know how we got to 5 years. It seemed like it was longer than that, a year ago. So which direction are we going in, and what are you seeing for warranties?
So what we're seeing is that you can get a warranty for any length of time that you want. With lithium ion, if you're putting in a system day one and you want it to perform, so your specifications say at year 10, I want this system to provide so much megawatt output at so many megawatt hours. What they'll warranty that, but you will pay for it, either in a way of they will allow space in the units in the building containers to add batteries as the capacity fades, or they will just say we're going to do a complete change out at year 10, because what they're really saying is, hey, we think our lithium ion batteries will last 10 years, and so they're adding that into the warranty.
Okay. So another question has to do with UL listing, and you had a slide, slide 19, where you talked about UL listing. The person says that, well, he's commenting that it's not correct that the system must be UL listed, and saying that what the requirement is that the system has to be tested and listed, but that can be done by any NRTL in the country to any standard. And then he says UL standards can be tested by UL, CSA, Intertech, etc. So can you clarify on that what's required in terms of UL listing and testing?
So I'll jump in, and Ben might want to add to it. He's correct. You can have any testing laboratory that you want. However, your authority having jurisdiction might tell you which one they will accept. And most of them, probably all of them, accept UL. But I wouldn't say all of them accept others. That's why you need to have that in place you have to have your AHJ in place early on so they can tell you who they're going to accept or not. And there's a lot of things going on right now, whether, you know, the 90, I'm not going to say the number because it's slipping right now, but, you know, there's some UL listing now for storage systems behind the meter that basically involves the a system, which is the inverter and the battery. Some of the batteries now, it used to be they would have a sticker. Now they're getting UL listed, which is a change. So it's an evolving process, but the questioner is right. There are other testing agencies, but be careful of what your AHJ will allow.
Okay, thank you. Here's a question on grid-connected and islandable systems. The question is the unified BESS control, that would be the energy storage, battery energy storage system control, worthy in the field instead of using two different control architectures for each operating mode? I'm assuming that means grid-connected versus islanded.
So one unit should, the one unit will handle both. Ben, you want to add to that?
Yeah, you should have a controller that knows that when it's connected to the utility, it can do like a current source. It may be a voltage source type energy storage system, but once it loses voltage from the utilities, kind of go into its emergency, it can do what it needs to do in microgrid. It might become grid forming, a voltage source, giving power over to the critical load, or it might be working with, you know, a generator startup, and all it's doing is a grid stability type mode, where it's just looking at a frequency and voltage, and it's just maintaining, if you're in a view at 60 hertz, and at whatever voltage you are, so 1 per unit. So yeah, you should have one controller that does it all, and it can also go to an islanded grid mode if you are being controlled like a SCADA or a utility, and you lost communication there. You also need to have a default controller, but once again, it's all within one controller.
And you know, to add to that, a couple years ago, if you went to buy an inverter, not all inverters went to grid following to grid forming. But from what I'm hearing now, just about every manufacturer, inverter manufacturer, has an inverter that will do just that, and they will do it very quickly. We're talking cycles, or maybe even less than a cycle. Don't hold me to that number, but so I don't know, maybe that's what he was referring to.
Okay. Well, we have another question that's related to that. Somebody's looking for recommendations on a single-phase inverter. Obviously, we can't give a recommendation for a particular company, but the question includes some specific requirements that he wants it to be able to handle 70 kilowatts of PV, 207 kilowatt hours of storage, and 125 kilowatt generator. So without giving a specific recommendation for this or that company, you know, I assume that there is a number of single-phase inverters out there that can handle that kind of thing. Is there a resource that you can recommend for somebody who's looking to, you know, find equipment, find an inverter that can handle certain types of equipment?
I would say have him send Ben and I an email, and we can follow up with him. Because right off the top of my head, if I said one and I didn't say somebody else, I'd probably get a nasty email why I didn't include somebody else.
Okay. Okay. Do we have
maybe
emails
Ben,
up on the screen?
If you want me to add to that, I can just say start looking at Department of Defense forward operating bases. That exact setup what the question was about, they've been performing for years now.
Okay. Well, there should be some public information about that, I would assume. Do we have, okay, there. We have, so we now have Dan Borneo's email on the screen. So if you want to email and request, you know, a link or a resource. There you go.
And as soon as I'm done off this call, I'm going to jump back on my boat and go fishing.
All right. Okay, let's see. Another question. What types of standards exist today for electric utilities to track energy storage system installations? For instance, PV systems usually require the electric utilities to inspect the PV system prior to signing off to completing commissioning. I would assume it's the same thing. They both have to be interconnected, right?
Ben, I'll let you answer that one.
Yeah, they are interconnected. Standards are just, you'll have to go through the list to see which standard applies to what you're doing. I mean, it is a sign-off of the PV systems, and they do have each, it's going to be kind of a case by case for energy storage because they do have different technologies involved. So you'll have to go through the list that was provided. Also, you can go back to that list that was in the slide that shows all the different standards, regulation, and codes that we have that you can use to sign off on an energy storage system being attached to your utility.
Okay, great. That's the list that you provided on the slide. And by the way, these slides will be available after the webinar. They'll be posted to our website. So if people are looking to get, okay, I see we have the list up on the screen, but it's rather hard to read. If you're looking to get a closer look at this or to go back and review these slides, they will be available. Okay, next question. Any good resources for lithium-based battery fire protection? I know we just had a big conference that Sandia hosted on battery safety and standards and codes. What's out there in terms of resources for fire protection?
You know, Todd, what I would suggest is somehow we put up that link to the information from that workshop for general discussion purpose. But you know, to add to that, what I learned from that workshop is this. So, well, I've seen projects that have FM200. I've seen projects that have water. I've seen projects that have both. I've seen projects that have neither. So when neither, start with that one, basically they're saying that the battery, the module, has this encapsulation foam that if it heats up, it basically smothers the fire by expanding and just, you know, encasing the battery in this foam. What we saw at that workshop was that if a battery goes, if it ignites, there's really not a lot you can do with it. The FM200 is an oxygen depleter. Well, if there's oxygen getting into the system, into the area, then it's really not doing that much. It will put out the fire initially, but as the oxygen gets back in there, it will reignite. Keeping the battery cool with water is probably like the best thing. So some people might say, well, I'll put the fire out with the oxygen depleter, and I'll keep it out with the water, keeping it cool. And so that seems to be like, you know, if you read all, you know, as we were inundated with presentations on lithium-ion battery fires, that seemed to be the general consensus of the best method. But the best method is actually to control it so it never catches on fire. Usually the fires are started either by overcharging or over discharging, and the lithium ion does not like either one of those situations. And if it gets too cold, that also, you know, the lithium starts plating out, if you will. Though that's more of a capacity fade issue than a fire issue. But so the big fire issues, if I was paying enough attention at this workshop, was either overcharging or over discharging, which is all about the controls.
Okay, thank you. And I was at the workshop as well, and one thing I do recall vividly was that there is sometimes venting of flammable gases that can reignite even after the initial fire is out. And the comment there, I think, was ventilation is really important to get that, clear the flammable gases out of the enclosure so that you don't have reignition problems.
So this is not part of the question, but you know, I'll play Kellyanne Conway here. One thing is that smoke exhaust. A lot of places don't really have smoke exhaust, which is an exhaust system that only comes on in the event of a fire. And it's usually after the fire is put out, then they exhaust the area so the first responders can go in. So that's one of the important things, and that might also help with exhausting any gases from the battery.
Okay. We have time for a couple more questions here. We had a couple questions on your comment about UPS systems, and people are asking which energy storage technologies ramp up in seconds to meet UPS needs. Somebody else wants to know, can an energy storage system respond fast enough to replace a UPS system? Have you seen projects that do this? Seems like a popular topic. Can you expand on this a little bit?
Yes, I would love to. So yes, they respond as they're an inverter, just like the unidirectional, bidirectional. It's the same inverter. It's just different configuration. So yes, they can respond sub-cycle. And my email went away, but email me. I would love to talk to you about it. So have I seen situations where they actually say I'm doing both? I can't say that I have, but I am really looking to get involved. Ben and I are looking to get involved with a project where we do just that, because I think it's relative. Now here's the problem. Here's the problem with that. You want that energy storage system to be available whenever you need it for your critical load. So you have to be careful in the design that when you're using it as an energy storage system, the other 98% of the time, the other 2% of the time, or 0.2% of the time, whatever it might be, it's going to be available for you if you need it. That's the trick. But I would love to talk to anybody who is thinking about doing that to discuss that. Actually, I was at an IEEE meeting where we gave a presentation, and I talked about that. And rumor has it from some of the people there that there was a lot of buzz over the, I call it UPS Plus, but yeah, there might be something there. There might be something there, and I'm willing to discuss that more.
Okay, great. Well, it's a good segue. You mentioned IEEE. I think this is going to have to be the last question. Can you address requirements for IEEE 519 compliance?
Ben, help me out.
Yeah, let me, we're going back up again. Let's see. So I get all my standards jumbled around. I don't think I can, if he wants to email me, I can talk to him about that question. Or give us his day, and I can talk about the meeting IEEE 519 or standard there.
Okay. All right. Well, unfortunately, it's a quarter after, and I think we need to wrap this up. Thanks to everybody who participated. Again, sorry about the glitching with the vocals. Not sure what was going on there. webinar will be posted in its entirety on our website, in our webinar archive. And thanks again to Dan Borneo and Ben Schenkman from Sandia. Samantha, we have some upcoming webinars. I know we have one coming up March 13th. This is another Sandia-related webinar under STAP, which is comparing the abilities of energy storage, PV, and other distributed energy resources to provide grid services. That's going to be basically looking at things like ancillary services and frequency regulation and so forth, and how you can, what the different distributed energy resources available can do to provide those services. And then we have some other related webinars that are not STAP, but they're perhaps of interest to this audience, and maybe Samantha, you can go over those quickly.
Sure. So, like Todd said, we do have a lot of webinars in March. Next Thursday, we have a webinar presented by CESA's Sustainable Solar Education Project, and the topic for that one is Solar Plus Storage for Low and Moderate Income Communities. This is actually presenting on a report that Todd wrote for CESA. And then we've got a Resilient Power Project webinar on with a guest speaker from JLM Energy. This is for a solar storage industry perspective series. And finally, we've got a webinar presenting some tools that we have here at the Clean Energy States Alliance and our partner organization, Clean Energy Group. So that's on Thursday, April 6th. It's tools for building more resilient communities with solar plus storage. So if you are interested in joining us for any of these webinars, you can go to cesa.org/webinars to read some more information and to sign up.
Okay, thank you. And with that, I think we're going to close out this webinar. Thanks again for everybody who came, and thanks to our presenters. We will see you next time.
Thank you.